So let's see what the manipulation is. So the manipulation is interacting with the environment and modify it using a robot so that we can perform some useful tasks. So those useful tasks can range from very simple tasks such as pick and place an object, as well as very complex tasks such as fasten two car parts of a chassis. So as you can see in the animation down below, this is what we are basically doing in robot manipulation. First, we define the initial pose of our robot, which is the initial position and orientation at a given time. And we plan our motion from starting from that initial position to an end position. So let's look at this nice video captured at Amazon Picking Challenge in 2016. So as you can see, this robot manipulator first detects the object of interest. Using the perception, and then it will reach out to that object to pick it up. So once it picks the object, then it can place it in another location. So this is what we are doing in manipulation. So let's see how this can be done in real life. To make this easy, we can divide the entire manipulation task into several functional modules. We need a functional module to sense or perceive the environment so that we can get information about where to go. Those information will then be fed into our motion planning module, which returns several waypoints indicating to the robot so that a robot can navigate it to its final destination. But that's not enough, isn't it? Because we need to ensure that those waypoints are collision-free and safe to robot to travel. For that, we have our collision checking module, which refines those waypoints such a way that our robot won't hit any previously known obstacles, as well as the newly detected obstacles in a dynamic environment using environment sensing. Once those waypoints were refined and we get collision-free waypoints, those waypoints will be fed into our trajectory processing module. Inside this module, those waypoints will then again be refined or updated with our timing information. So those timing information will be in a form of velocities or acceleration values. Finally, those waypoints will be used to execute our planned motion. So this is how we are doing manipulation in real life. There are many different libraries developed by researchers out there that can be used to build each of these functional modules. For example, we can use cameras like interior sense and sensor or even LiDAR sensors to develop our environment sensing module. For motion planning, we can use libraries such as OMPL, CHOMP, and for collision checking, flexible collision library or bullet physics library, and also IPTP, iterative parabolic time parameterization, or TOPP, time optimal path parameterization algorithms for trajectory processing. So finally, for motion execution, we can either use a real robot with ROS drivers or a simulation engine such as Gazebo. So even though we have a bunch of these libraries out there, we have to ensure that we can integrate all of these things together so that we can achieve our manipulation task. So isn't that fantastic? If there's something out there that can do that for us, so there is, it is called Movelt. So Movelt is an open source software library that is designed to do manipulation tasks. Your robot, your manipulator can either be fixed or mounted in a moving platform. Movelt is no different at all. So to install Movelt, you can use the following command. And as you can see, you just need to update the final part of the command depending on your ROS distribution. In here, I'm using ROS kinetic distribution to install. Movelt can be used as a platform to configure and use various configurations related to robot manipulation also. Let's see how Movelt helps us to do our manipulation tasks. First, it maintains the information consistency between our ROS application and the functional modules we discussed earlier. And also Movelt ensures that the libraries I mentioned earlier will work seamlessly with our robot application. Uh, Moveit actually communicates with collision checking and motion planning modules I discussed earlier, so that it can report and request alternative motion plans in case of collisions. Moveit also takes care of hardware limitations such as joint limits and maximum and minimum joint angles, etc. And also Moveit aware of any environment change happening in a dynamic environment. So because it keeps track of the current robot state as well as the environment while performing such manipulation tasks. Finally, Moveit actually gives feedback to its hardware or the simulation engine, such as Gazebo, to inform whether the manipulation is done. That's a lot of work, isn't it? But as a Moveit user, we can only see a one single ROS node named Move, which provides many ROS services and APIs to access those services. We will see this move group node in a later demo. To configure this move group node successfully, we need to take care of few other parameters such as URDF, robot description, you learned about earlier, and SRDF, robot semantic description, which consists of information about robot poses and joint limits, plans, planners, etc. So how we can configure all this? For that, Moveit provides a very nice, simple GUI interface called Moveit Setup Assistant. So now we'll see how we can use Moveit Setup Assistant to plan motion for a serial link manipulator in a factory environment in the demo video later. But you have to understand that you don't necessarily need to understand every bit of information that you're about to see, because the main idea behind this demo is that to let you guys know about what are the capabilities of Moveit that we can use in our own robotics project. So let's enjoy the demo. So as you can see, this is our Moveit Setup Assistance interface. To get started, first we need to import our URDF file, which is our robot description file. So here I'm using a ready-made URDF file, which consists of two robots with a conveyor belt also. So next we can go to self-collision section, which generates a collision matrix. So the default collision matrix generator will searches for links in robots that can safely be disabled from collision checking, so that our motion planning processing time will be optimized or reduced. So as you can see, in this matrix, there are 4 columns like link A, link B, and the indication whether it is disabled or not, and the reason for disabling. So once you generate the collision checking matrix, we can move on to our virtual joints. So virtual joints will be defined so that we can attach our robot to our world frame. So if you have a robot mounted on a moving platform, these virtual joints will be very, very useful. So we can define 2 virtual joints for each of those 2 robots. Once we define our virtual joints, then we can move on to define our planning groups. From now onwards, I'm denoting those robots using the planning groups. So we have to define 2 planning groups, one for each robot, with several algorithms like OMPL planning algorithms. You can later know all those things while you are deeper diving into the subject matter. So while defining those planning groups, we have to indicate what is our base link and also our tip link or our end effector. So we can do the same for our robot too. So now we have 2 planning groups, one for each robot in our factory environment. Then we can define our robot poses. As I said earlier, pose is a position and orientation of a robot in a given time. So here we are defining one robot pose for each planning group. Here we are defining R1 up robot pose for robot 1 planning group. And we can do the same for robot 2 planning group also. You can see those values are in radians. So once you define those robot poses, we can click that Move It button over here to check whether those poses are working as expected. As you can see, that movement is not so smooth because Move It uses a fake controller to move those robot arms to their desired poses. So it is our responsibility to create a separate controller so that we can move those arms very smoothly. So here there's a section called ROS control. So this section. So in here we can actually define our ROS control, but we don't necessarily need to do that in here, or we can do it manually later. So once we are done with all the configuration, we can generate our configuration package here by clicking the generate package. So now our configuration package has successfully generated. So now we can go to that configuration package to check whether they have generated correctly and with the desired folder items. So here, as you can see, there are two main folders, config and launch. So inside the launch folder, you can see several launch files. You don't need to worry about those launch files just yet because you will be creating your own launch files later in the hands-on session. So when we go to the config folder, you can see several configuration files in YAML format. So I need to show you several important files that we can see in this folder structure. So one is the fake controller. As I mentioned earlier, this is the controller that Moveit uses in case our controller is not present in our folder structure. So in the controller, this is the controller I created manually with only difference of action namespace and type. So those are the two fields that is responsible for the smooth motion of our robot arms. So once you are done with the controller, Moveit knows that we have defined our own controller, then it uses this controller instead of that fake controller to move our robot arms. So next, let's move on to our SRDF file. As I said earlier, SRDF consists of robot poses. So as you can remember, we have defined two poses, one for each planning group. So these are the two poses that we defined earlier, R1 up for robot 1 planning group and R2 up for robot 2 planning group. Finally, we can move to our move group.launch file, which launches the move group node. So here, as you can see, there are a lot of launch files called inside this move group.launch file. So this is the move group.launch file. So there are several other launch files over here in the launch folder section. So we'll be using one launch file to run our gazebo environment to give several commands to our robot arms to see them working. So let's launch our gazebo environment using one launch file. So this might take a bit. Then we can see our factory environment with two robots. So this is our gazebo environment. So as you can see, we have our robots here. So let's try to move those robots as we defined poses and controllers earlier. So for that, Moveit provides us the command line interface named Moveit Commander. So first, run the Moveit Commander using this command, rosrun command. So once we launch the Moveit Commander, we will be able to see a prompt. So this is the prompt. So using the help command, we can see all the commands available for us to use. So we'll be using a few of those commands in this demo to check the robot moving. So here we can see go command, execute command, pick, place commands, and several other commands too. To execute commands for a robot, we have to mention what is the planning group that we are considering first. For that, we can use command with the planning group name. In this demo, we are executing command for robot 1 planning group. So we can write the command as use robot 1. And then we can use go command to execute commands for this particular robot. So go R1 up means it executes the pose 1 for this robot 1. So as you can see, the motion is very, very smooth because we have already defined our controller instead of that fake controller. Even though we have not defined any poses for the end effector or the tip of this robot, we can actually use go down 0.2, go up 0.1, or any measurement to move this end effector too. So this is tedious, right? Because we don't need actually to execute each of these commands separately in a commander. For that, Moveit provides us a shortcut. So we can actually create a file separate file containing all the commands that we need to execute in order, and then load the file to move it command. So like that. So this is the file I created with all the commands that I executed earlier separately. So once you created those files, then we can launch the command again. And then using the load command, we can load the file and execute all the commands that we mentioned in that file. So as you can see, our robot moves as before. So let's say if you want to get information about the current pose of the robot. So in this pose, for example, for that also Movelt provides a command named current. So using that current command, we can get information about the current pose of the end effector. So our end effector is vacuum gripper 1 suction cup. So the pose of this vacuum gripper 1 suction cup can be listed as here using XYZ values and also orientation as fall, pitch, yaw values. So this is a very, very basic movement of our robot. We can actually execute somewhat more advanced motions for each of those robots. For that, we have to create our own ROS node to execute those commands by using the configuration package we generated earlier using Movelt Setup Assistant. You will be developing your own ROS nodes in a simple ROS nodes in a later hands-on session. But for now, I'm using my own ROS node we developed earlier. So first, let me execute the ROS node. So here we can use the ROS run command, execute the ROS node. So once the execution is done, you can see very nice motion of the robot one. So you can do the same once you understand the basic concepts of ROS node, ROS launch files, and move it. So as you can see, our robot mimics the exact motion we saw earlier in the robot won the Amazon picking challenge. Just like that. So that's pretty cool, isn't it? So that's just a simulation. So here, let's see how we can do that in a real robot. So here in this video, you will be seeing how ROS was used to manipulate a real robot created using 3D printed parts with several chip servo motors and a controller. So if you have your own robot with 3D printed body parts and also chip servo motors as your joints, you can use ROS. You can follow the same procedure earlier to move the robot. So let's enjoy this for a bit. So I'd like to say, don't stop right here. Do it by yourself and dive deeper into this subject, dive deeper into Movelt, because as Dr. Pesha mentioned earlier, there's a very big community that you can get help from. So you can use those resources and as well as very nice documentation in each of these parts. So you can use all of those things to improve your knowledge and use the robot for your ROS for your own robots. So now let's say you have your own robot and you have coded that robot, but you don't know how to interface that robot with ROS. So let's ask that question, Bhanuka. Bhanuka, over to you.